I'm going to talk about FHE, fully homomorphic encryption, a little bit, and mainly multi-party computation, but we're going to be talking about how we compute on encrypted data. So I'm going to touch on what MPC is, I'll touch on what FHE is, we're going to look at a bit about coding theory, recap error correcting codes a little bit, and then we're going to look at how we can build MPC protocols out of error correcting codes, and then if we're very lucky, and I mean very, very lucky, or not, depending on your point of view. At the end, we'll talk about how we can combine the two together in something called speeds, but maybe not. Okay, so what is multi-party computation? Is I have a function, I have a bunch of parties, multi-party computation, that's clues in the title, got a bunch of parties, P1 to Pn, and they want to compute some function, f, of their joint input, and the security requirement is that they should, once you've got the output of the function, you should learn nothing about the inputs bar what you could compute from the output. Yeah. So if I'm computing argmax, which is like the famous millionaires problem, and I've got a bunch of people here who earns the most money. I don't know, Bart earns the most money, say. So Bart's going no. So everyone learns that they earn less than Bart, but you don't know how much Bart earns. You don't know anything else about the function. You don't know about the amount of money that the person sitting next to you earns, or something like that. Okay, so that's what we want to do. And we have and unlike encryption, where you have Alice and Bob, and Alice and Bob are in some sense meant to be the good guys, and the bad girl is, or the good guy and girl, and the bad girl is sitting on the wire in the middle. That's Eve. Okay. In MPC is that the people actually doing the protocol, they're also bastards as well. So everyone's a bad guy. So apart from one, you must always have one honest party. Okay, so at least one honest party. Okay, so we have this set of bad people, and they're a subset of this total set of players. So imagine like you've got an encryption scheme in which Alice is the bad girl. Okay, so it's kind of a bit like that. Okay, so we have examples in the real world, and you cannot have an MPC talk without talking about Danish sugar beet auctions, because the Danish sugar beet auction was the first example of a deployed MPC in practice, and that was about ages ago now, about 15 years ago. There's a company in Denmark called Partises. There's a number of startups in this space, and Partises is a startup in Denmark that markets MPC solutions to manage market mechanisms, so in particular sugar beet auctions, but they also do electricity auctions and other power auctions and things like that. There's a company in Estonia called Cybernetica. It's a very old company, but they have a division called ShareMind, and they produce an MPC database which allows them to conglomerate data from various sources. They've done stuff between the Department of Education and the tax authorities. They've done all sorts of other European projects, and they market a database there. There's what's called the Jana database, which is produced by a company called Galois with the main component here. This is a part of a DARPA-funded project called Brandeis that we're involved with, and this uses the MPC software from Leuven. This is another database, says it in the title already. And then there's for those of you who don't like HSMs, you can virtualize your HSM and produce an MPC version of an HSM called a virtual HSM, and that's produced by a company called Unbound Tech, based in Israel. And there's another company in Denmark producing a key management system for the cloud based on MPC called Sepia. So there's a number of applications, and there's a number of other companies in this space. I haven't mentioned Baffle. In the FHE domain, there's a company called Enveil, there's a company called Duality, and I forgot what the new one is in Paris, but I was told it last week, but I can't remember its name. Anyway, but there's a number of startups in the space marketing products based on secure computation. So what is secure computation? So I told you what it is that we want to compute a function. And now what properties do we want? Well, we would like the function output to be correct. So if everybody executing the protocol keeps to the protocol, we would like the actual result of the function to be computed. Yeah, that's kind of like a basic correctness requirement. Now, passive security is that what you have is that you allow this is what's called honest but curious adversaries. The adversaries are honest, they follow the protocol, but they're kind of curious, they really want to find out how much Bart earns, right? Yeah, but on the other hand, they do want the protocol to proceed, so they'll do what they're told, but at the same time, they kind of want to look over the wall and see what the other person's money is, or say. Okay, so that's what a passive adversary is. Now, the other point is a robust active security. So you often see the literature say active security and passive security. Now, there's two forms of active security. There's active security with robustness, which means that if you're the bad person, you can be the bad person for today's talk, okay, that you now deviate, you've been elevated to an important person, so you're allowed to deviate from the protocol. Now, in a robust protocol, everybody else is fine with this, because although he's going to be horrible, we can ignore him, okay? That's what a robust protocol is. It means that we still compute the output of the function correctly. Now, that's actually quite hard to achieve. So what we try to do is we actually make things easier in cryptography. If we can't do something, we make it easier to do. So the other form of security you get is active security with a bolt, which means if you cheat, everybody else goes, "Miss, he's cheating," and then then we all just stop, yeah? So that's what active security with a bolt is. See, so you just have to go, "You're cheating," and just give up at this point. Now, it turns out, in reality, where most of the commercial applications we see, people only care about active security with a bolt. Academically, people mainly in the past used to care about robust active security until they realized there was more money down here. And then they went, "No, we're not interested anymore." Okay, so this is kind of more academic usage. And also in terms of reality, when people academically go, "Oh, we want multiple parties," this means large numbers of parties. Most applications are, the large numbers of parties are 2 or 3. So very rarely is there more than 3 in any real application. Okay, mainly because in commercial world, it's quite hard to coordinate a large number of organizations, yeah? Getting 2 to decide to do something at the same time is difficult enough, let alone 3 or 4 or 5. Okay, so this is what multi-party computation is. Correctness, and then 3 notions of security. Weakest is passive, strongest is robust, and the one we usually go for is active security with a bolt. Okay, so not only do we have that, but we have how many bad guys do we have? So we've got a large number of people in this room, and then we've got to decide how many bad guys are we going to tolerate. Are we just going to tolerate one person down the front being bad? Are we going to tolerate everybody on this side of the room being bad, or are we going to tolerate everybody bar you? You're the only honest person in the room. Okay, so there's different things. We can have a very small number being corrupt, half of you being corrupt, or everybody corrupt bar one. Okay, so this is what's called the adversary structure. What we're interested in. What level of adversary structure do we want? We don't even know that she's the honest person. It could be Manuela's the only honest person, or unlikely, or I don't know, or Svetla's the only honest person. So we could have we don't know who's honest or dishonest, but we know what the structure is, how many people are in the set of honest parties, okay? And then there's 2 different notions of security. There's static security and adaptive security. Now, in static security, the adversary is sort of meant to come along and go, "I'm going to corrupt you, and you," and then we execute the protocol. Okay? In adaptive security, the adversary comes along and you execute the protocol and he goes, "Ooh, I like what you're doing, I'm going to corrupt you." And then a bit later on, "Oh, what you're doing is quite cool, I'll corrupt you." So you adaptively corrupt people as the protocol goes on. That's what's called adaptive security. No surprise. Generally, again, because it's hard, we don't do adaptive security. Yeah. So people care about static security, and then they do a fudge to try and, in the real world, bootstrap that into some form of adaptive security. But it's not what theoretical cryptographers call full adaptive security, because that's actually really quite tough. Okay, so we're going to be concentrating mainly on static security for this talk. Okay. And then, just to confuse you even more, there's 2 flavors of MPC. There's information theoretic MPC. Now, information theoretic cryptography is cryptography which is secure no matter how powerful the adversary is. Even if the adversary could build the biggest computer in the universe and expend all of the energy in the universe to solve a hard problem or to break the cryptographic protocol, it is still secure, okay? No matter how big the security is. So the one-time pad is information theoretically secure. And we can achieve quite a lot with information theoretically secure protocols. So we can obtain passive security if up to half the room is corrupt, okay, with information theoretic. So no matter how powerful half the room are, we'll still get a secure protocol. We can get robust active security if up to a third of the room is corrupt. That's related to Byzantine generals like standard fault-tolerant computing results, yeah? And then we can get active security with vault if up to half the room is corrupt as well, in the information theoretic sense. Now, if we want to, now normally we don't really in the real world care about information theoretic security. We don't use the one-time pad in the real world. We're prepared to have computational security. We're prepared to have security which is only secure up to a given bound on the resources of the adversary. So we give a computational bound on the security of the adversary, on the power of the adversary, and we say that's computationally secure. Now, if we assume that, what we've done is we've assumed a less powerful adversary, so we can now achieve more. Yeah? So less powerful adversary, we can do more. So what can we do? Well, we can get passive security if we have up to n corruptions. So in other words, you're all right, yeah? If it's just you, we're fine, okay? Whereas if we were information theoretic adversary, all bets are off, yeah? We can get a robust active security if and only if t is less than n over 2, but we can get active security with a vault and you're still okay. Yeah, so you're doing well here, right? So we've got active security with vault, and we can even give security if all of you are corrupt bar 1. Okay, so this is quite good. So assuming the adversary is computationally bounded, we can do really all that we ever need to do. Okay, so this is in the real world, that's what we assume. Okay. Now that's MPC. Now FHE is slightly different. It's an encryption scheme. It's in the title, fully homomorphic encryption. So what's an encryption scheme? Well, it's a public key encryption scheme where we have the message space is in some sense a finite field-ish. Okay, integers mod p. Don't worry about the details, but it's fine. There's lots of lies in this talk, by the way, or details under the carpet. Okay, so it's an encryption scheme, so it's very, very important that when you encrypt a message under a public key and then you decrypt it with the secret key, you get the message back. That's important property number 1, okay? Now, important property numbers 2 and 3 with a homomorphic encryption scheme is that there's a special function called add, which allows you to add 2 encryptions, and when you decrypt, you get the sum of the underlying plaintext back. And similarly, there's an operation mult, which you apply on ciphertext, and it allows you to multiply 2 ciphertexts such that when you decrypt them, you get the product of the underlying messages back. Okay? And this, if we have this property, we're said to have what's called a fully homomorphic encryption scheme. And this, a fully homomorphic encryption scheme, allows us to compute on encrypted, one person to compute on encrypted data. Yeah, because you just encrypt the data to him or her, they just do all the operations, add and multiply, and then you've got whatever the encryption, you've got the encryption of the function that you've got, that you wanted, yeah? Now, obviously, for those who were paying attention yesterday, this can't be in CCA, or it can't be AEAD, because it's clearly malleable, yeah? This is kind of like Crypto 101, that this is clearly not an in CCA scheme, but we can have in CPA homomorphic encryption scheme. So, you know, and you can build these things. Surprisingly enough, these things actually exist. Weirdly, okay, so if you wanted to use what's called textbook RSA, that's the old-fashioned RSA function that you see in bad textbooks, better textbooks are available, that you can have, so you take textbook RSA, now that is multiplicatively homomorphic. You can take 2 RSA ciphertexts, you can multiply them, and you'll get the product of the RSA of the underlying messages. Now you could do, there's another encryption algorithm called Palia, which is additively homomorphic. You can take the encryption of 2 ciphertexts, you can add them, and you get a ciphertext whose underlying message is the sum of the 2 underlying messages of the original ciffertext. The problem is coming up with an encryption scheme which is both additive and multiplicatively homomorphic. Okay, so this was actually quite difficult, And the reason why we're interested in this is because add and multiply are universal gates. So once we can compute add and multiply, in theory, we can compute any function. Yeah, so this is, it's like computer science 101. Okay, and so this thing was kind of like thought, does it exist, does it not exist, whatever. And then Craig Gentry in 2009, he had his result that you can create a homomorphic, fully homomorphic encryption scheme. I'm not going to go into the details of how you do that because that's rather complicated. Okay, but the FHE and MPC are kind of linked, which I'm going to kind of give you a very quick overview of why they could be linked. Okay, so if we think about homomorphic encryption schemes, if you could take any function and you write it as adds and multiplies, which you can do, that's computer science 101. Now we take a bunch of ciphertext encrypting some messages, M1 to MN. And now, because it involves adds and multiplies, we can create a function eval which applies the additions and multiplications of the underlying function to the ciphertext such that we can produce a new ciphertext that when we decrypt it gives us the function evaluated on the points we started with, which is kind of cool, yeah? So the idea here is that you can outsource any computation. The server gets some ciphertext, so the kind of thing in the original academic papers, which of course are mad because they're academic papers, say we can now outsource Google search because we can encrypt our search query, send it up to Google. Google could homomorphically evaluate the search query and then give you the encrypted results back. That's what you can do in theory with only polynomial cost in the resources that you would need over what you would be able to do it in the clear. That polynomial cost has a very, very, very large constant, which means that if you wanted to do it for a Google search query, you would die, the universe would die before you actually got your result query back. So it's not very practical, but it's polynomial time, so it's fine. Okay. So yeah, but you could do encrypted search is the idea, and it would be really cool if you could make this go faster. Okay. Now that also allows us to do MPC in the following way. So imagine we now kind of just extend the FHE scheme a little bit, and what we have is instead of one secret key, let's have n secret keys, one for each party, okay? Such that together they can produce a partial decryption which we can then combine to do a decryption. It's got a distributed decryption facility. So my favourite three people in the room here, right? So we've got 4 keys, and you do a bit of decryption, you do a bit of decryption, you do a bit of decryption. So we put all the stuff together and we get the message back. Okay, this would be cool. This means they won't decrypt unless they've got your key, so you're happy, and you all have to come together. Yeah. So we're protecting you all the time. Yeah. Okay. So this is a this has got a distributed decryption. So imagine we've got that, which is easy to do. So don't worry about that. And now we have this amazing MPC protocol. So the 4 of you want to compute some function in MPC. So what you do is you just encrypt your inputs. You then just exchange your ciphertext. You now apply the evaluation function. So you've now got an encryption of the result you want. And now you just do the distributed decryption. Yay, we're done. MPC's done. Okay, end. And this is rather cool because all we have to do, we have exchanged the ciphertext. That's one round of communication. And then we exchange the partial decryptions. That's another round of communication. All done. Okay, so this is very, very simple protocol. But it turns out this was not how you would want to build a business because it's going to be very, very slow. So what we really want is we've got an MPC because we've got FHE. The trouble is it's very slow. If we try to do this, it will take a long time. So what we want is we want something, and it's only passively secure. So, sorry, I can't do everything. Yeah. So, but later on we'll make it okay for you, right? So, but we'd like a more efficient solution, and there's 2 ways of doing this. There's what's called an approach based on garbled circuits, which dates back to the 1980s. Yuta Yao. And he won a Shearing award for this, and other stuff. And then there's an approach based on linear secret sharing schemes, also dating back to the 1980s, where Goldwasser and McCallie and others worked on this, and they also got a Shearing award. So it's a kind of, If you want to win a Shearing award, which is like the Nobel Prize of computer science, it's really good to work in cryptography. Your probability is far higher to get a Shearing award if you work in cryptography. And if you work in cryptography, you're more likely to get a Shearing award if you work in MPC. by the probabilities it's going to turn out. Okay, so anyway, so we're going to do the linear secret sharing scheme based approach. We're going to do a quick recap of Reed-Solomon codes, which one presumes you've all seen at some undergraduate lectures in the dim and distant past, or not so dim and distant past, depending on your age. So we're going to have Reed-Solomon codes, and they're going to be related to what's called Schmier secret sharing. So a Reed-Solomon code is given by, basically it's given by two integers, n and t. So think of n as the number of people in this room, and t the number of bad people eventually we're going to tolerate. So that's this half of the room, okay? Okay, and so what we could do with a Reed-Solomon code is we can detect n minus t minus 1 errors, but we can detect more than we can correct, okay? So that's the kind of basic point. And it's going to be over some finite field with q bigger than n, okay? So the basic idea is that you take some polynomial, this defines a code word, the actual codes are given by the evaluation of the polynomial at different points, and we think of f as the message and c as the code word, as the encoding of that message. Yeah? So this is standard Reed-Solomon stuff, and we can transmit different bits of information. So it looks like this. So if we want to transmit this lovely curve, what we actually do is we've got 7 parties here, and we transmit this point, sorry, it's 7 data points here, this point, this point, this point, this point, this point, this point, this point. Okay, that's a Reed-Solomon code. Now, if there's how do we get data recovery? Well, to get data recovery, we've just got to recover the coefficients of the polynomial. That's just a linear system, that's matrices, okay. If you really don't like linear systems and matrices, that's just Lagrange interpolation, so that's also easy, however you want to look at it. So that's nice and simple, okay. Now, if there was a problem in your error correcting code, or error detecting code, so for example, we've got this lovely curve here, and one point is received bad, yeah? We would detect this because that's clearly not that if you think that's a cubic function, there's no way you can get a cubic function through these points. Yeah? So this is clearly an error. So that's error detection. Good. And because we've got quite a few points, we actually know we know that this point should have been up there. Yeah? So we can actually do error correction as well. So this is basically the idea of Reed-Solomon. So I'm just skipping this because it's kind of boring. And you can recover stuff by, if you wanted to actually do full recovery, you can go through all proper subsets, and there's Verticamp-Welsh algorithm that you've all probably learned, yada, yada, yada. See any decent textbook. Okay. Okay, now how is this related to Schmier secret sharing? Okay, because we could use this error correcting code, or error detecting code, we're actually going to be more interested in error detecting, to define a secret sharing scheme. So what we do is we map secrets to the polynomial which has the secret as its constant term. Okay, so if I go back to my picture, this picture here, what I'm going to do, this polynomial goes through, let's call that minus 18. So minus 18 is my secret, okay? It's the constant term, it's the point where the polynomial hits the y-axis, yeah? Okay, that's the secret I'm going to encode, but then to encode the secret, I'm going to distribute it amongst the n parties. So I'm going to give you the function at 1, you the function at 2, you the function at 3, the function at 4, and so on. Okay, so everybody gets the function evaluated at a point, and that is their secret share of the data value. Yep. And then using the Lagrange interpolation formula, we can recover the secret. Yeah, we just apply the Lagrange interpolation formula. And in fact, any t plus 1 parties, as long as they're honest, we can recover the secret. So that's kind of cool. And this is what's called Schmier secret sharing, and we can define what we mean by security. But the key bound is that the number of adversaries has got to be less than n over 2. Okay, so we've got to have at least an honest majority, and there's more of you on this side than there is on this side. Okay, so there's more honest majority. So that's the key, and this allows us to do error detection. Now, if we wanted to do error correction, so this would be the case where, so in the case where we have an honest majority, and it's at more than n over 2, this allows us to do MPC with abort. Because if you see an error, you go, oh, something's wrong, I'm going to abort. Now, if we wanted you to recover, we're going to need a third of you to be bad. So somewhere about here. A third of the, Bart's always in the bad section, okay? So we have this third of bad over here. Okay, so if we have that, then you've got enough data, assuming you're all honest, to recover, not only work out that these were the bad people, but you know exactly which ones lied, okay? So there's a kind of link between error correction, error detection, and the error detection and the robustness with a ball or active security with a ball or robustness that you get in MPC. They're very related, okay? Okay, so in general, we can define an arbitrary, don't just do this for Shamir, we could do this for an arbitrary secret sharing scheme. So we say something is a linear secret sharing scheme if we have the following construction. We've got some matrix, we've got m by d matrix and a vector v, a special vector v. And what happens is to share a value, we pick a random vector k such that s equals the dot product of v by k, okay? And then we also compute m by k, which is the share vector, and then we give different people the shares. So in how does this relate to Shamir? Have I got that on my next slide? No, not yet. Okay, so I'll do this now. So how does this relate to Shamir? So in Shamir, the m is essentially the van der Monde matrix evaluating the polynomial, and then we give each person, so to each row of the matrix we associate one person. So if person 1 gets the first row, person 2 gets the second row, and so on. Okay. So this map chi is a map from the rows of the matrix to the set of players. Okay. So this is a linear secret sharing scheme. It's called linear because it's to do with matrices, therefore it's linear. Okay. Okay. Now any set of parties can recover the secret if the span of the rows of I indexed by blah 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 contains A. So in other words, that basically you've got that this V is contained in the span of the rows that the set of parties kind of own. Okay, so because then you could take a subset of the matrix that depends on the set of parties A, and you'd be able to recover the secret. So nothing too tricky here. But the cool thing is this. Is that if you have a linear secret sharing scheme, you can compute any linear function. It's kind of in the title, linear secret sharing, linear functions, kind of like obvious, yeah? If it wasn't true, then there'd be something wrong with maths. Okay, so and we can do it without interaction. So let's suppose we've got two secrets, S and S dashed, which are shared. And remember, to be shared means that there's some hidden vector K and K dash such that the share vector is M times K and S dash is M times K dashed. And then, so what will happen is that you can think of S plus S dashed as being shared by M times K plus K dashed. It's just linear, I mean, duh, right? Okay, which because then S plus S dashed is going to be equal V, the target vector we had, dot producted with K plus K dash. So that's kind of easy. And we could also do arbitrary, so this allows us to add, this allows us to do arbitrary scalar multiplication. So if we use square bracket S to denote S is shared under this secret sharing scheme, then we can actually take a secret sharing of X and a secret sharing of Y and compute this arbitrary linear function for free. Okay? So linear functions can be computed for free if we have a linear secret sharing of the data. So this is kind of, this is a fact used quite a lot. So here's the example of why Shamir is a linear secret sharing scheme for homework or for the pub later or whatever you're doing later. You take the message M, sorry, not the message M, you take the matrix M. This is the matrix, the rows correspond to people, player 1, player 2, down to player N. We have the target vector V, 1, 0, 1, 0, 0. This is each player is associated to its row, and that's the Shamir secret sharing scheme. It's exactly the same thing. There's, we could think of full threshold. This is in the case where we're only caring about you being secure. Okay, so here it's another exactly the same case. We have M is the identity matrix, and now the target matrix is 1, 1, 1, 1, 1. Okay, and we associate each player with each row. To have a slightly more complicated example where each player gets 2 rows of the matrix, we have what's called replicated secret sharing, which is another way of doing a threshold structure where you have n parties and you tolerate up to 1 bad person. Okay, so here, this is the matrix for the replicated secret sharing with 1, 3. And so what happens here is we've got 3 players. We're going to take Elena, yourself, and yourself. So Elena will get S2 and S3 because she gets the first 2 rows. You've got the middle 2 rows, so you'll get S1 and S3. And there you've got S1 and S2. And the two of you coming together will recover S1 plus S2 plus S3, which will allow you to recover the target because the target is 1, 1, 1. So the secret is actually S1 plus S2 plus S3. Okay, so it's kind of very, very simple. Okay, so that's linear secret sharing schemes. So we're almost done. Because, remember, all we have to do is be able to do additions and multiplications. So we're halfway there. Yeah, so we're almost done with being able to compute an arbitrary function. Okay, so to be able to compute an arbitrary function, obviously we've got to take products. So how do we take products? Well, we just take a tensor product, which in this case is called the Schur product. Okay, so each party holds a sharing, which is their kind of, so it's in the replicated case, Elena had 2 elements. In the Shamir case, Elena only had 1 element. So we have different numbers of sharings. Now, when you take the Schur product of your local sharings, what you're doing is you take the tensor product, you multiply all the different components together in all the different ways, okay? So if you started off with 1 element in one sharing and 1 element in another, there's only one thing you do. You get 1 times 1 is 1. If you had 2 and 2, you end up with 4 things, yeah? So you take the tensor product. Now, so with Shamir, let's just we do something simple. Okay, so that's what we mean by taking the Schur product. And what's kind of cool is we say a secret sharing scheme is multiplicative if you've given 2 sharings of elements, so you've got a sharing of S and a sharing of S dashed, then you can produce the sharing of the product, sorry, not the sharing of the product, but the product of the things being shared is a linear combination of the local Schur products. Okay? So the thing you're trying to compute is a linear combination of the local Schur products. Okay? So this is what we mean by a scheme being multiplicative secret sharing. Okay? And it turns out there's a lot of multiplicative secret sharings out there. So for example, in the Shamir case, when t is less than n over 2, then Shamir secret sharing scheme is multiplicative. Now, why is that? Well, because if I gave you a secret sharing of S and a secret sharing of S dashed, where S was shared under F and S dash was shared under F dashed, then clearly the product of the 2 polynomials, what I want to do is I want to compute a product, yeah? So if I think about it, where's the chalk? Haha, here we go. So I have a polynomial f of x and I have a polynomial f dashed of x. I have the f of 0 equals s and I have f dashed of 0 equals s dashed. I have the degree of f is equal to the degree of f dashed is equal to, we're going to call this t, okay? Now, what I want is I want to multiply s times s dashed. Now let's do something really stupid, okay? And what I do is I compute, I'm going to call it g of x is going to be f of x times f dashed of x, okay? Because g of x, g of 0, is going to be s times s dash. So that's what I want. Haha, good, yeah, I'm happy. At this point I'm happy. But the problem is that, well, or depends on your point of view, is that the degree of t, degree of g, has just doubled. Yeah? But if I've got enough people, okay. But if I've got 2t is less than n, then the Lagrange interpolation formula, not applied to F, but applied to G, will allow me to recover the S times S dashed. Yeah? So if 2t is less than n, then Lagrange interpolation allows me to write the product S times S dashed as a linear combination of the local products. And the local products, so player 1, local product is f of 1 times f dashed of 1. Player 2's local product is f of 2 times f dashed of 2, and so on. Okay. So this is what we mean by a multiplicative secret sharing scheme. Okay. Now it doesn't say actually how I do the MPC to do the multiplication. It's just a property I need of the secret sharing scheme. But you can easily see that if t is less than n over 2, Shamir has this property. Okay. Okay, replicated also has this property. So remember, our replicated secret sharing scheme is I've got S is K1, I share S via K1 plus K2 plus K3, and I give party 1 K2 and K3, party 2 can hold K1 and K3, and party 3 holds K1 and K2. Now, if I imagine that I've now got K1, K2, K3, K1 dash, K2 dash, K3 dashed, and now party 1 is going to do all the multiple products of K2 times K3 dashed, K3 by K3 dash, K2 2 dashed by K3 dashed, and the other one, yeah, okay, I lost track, okay, but then if I do the product, I write it like this, I expand it like that, and then I group the terms like this. Now all of these terms here are a linear combination of the Schur product of party 1's term. All the terms here are a linear combination of all the products in Schur product in party 2's term, and this one is a linear combination of all of the products, bar 1, of all the terms in party 3. So this is also multiplicative. Yay! So this is so multiplicative secret sharing schemes are really quite abundant, you would think, except they're not, because its full threshold isn't. So. Sorry, you on your own. You're on your own at the moment, so I can't help you at the moment. Okay, okay. So if we have the multiplicative thing, this seems to be quite cool. And so it turns out that there's a very, very simple protocol which allows us to use this to produce multiplication in an MPC protocol. Okay. Now let's go back. So what we had was, we could compute linear functions for free. Yeah? Okay? So that's good. And we had that the product is represented as a linear function of the Schur multiplier, the Schur products, yeah? So what we're going to do is we're going to combine the fact that we've got linear functions for free and that the product is a linear function of the Schur products together. And this allows us to do what's called Maurer's multiplication protocol from, when was it, Tim? 2006. There we go. So this was done before, but in terms of a general framework, this is 2006. Okay. So let's assume we have a multiplicative linear secret sharing scheme. Okay. So we can compute linear functions for free. Then we can also compute multiplications almost for free. So what happens is step 1 in the protocol is as follows. Each party locally forms the Schur products of the parties share. So let's do this for our Shamir example. Suppose it's a 3-party Shamir example. So I want to compute the thing. Yeah. So I want to compute the S times S dash somehow. So what I do is we've got a secret sharing of S, which is f of 1, f of 2, f of 3, each given to each party. I've got a secret sharing of S dashed, which is f dashed of 1, f dashed of 2, f dashed of 3. Okay, so step 1 is I can produce the Schur products locally. So each party does this. That's step 1. Okay, step 1. Okay, we need some numbers. So let's call this Z1. Let's call that Z2. Let's call that Z3. Okay? Now, step 2 is I've got to express the product as a linear function of the Schur products, which I can do because it's multiplicative. So step 2 is there exists a linear function L such that S times S dashed is L applied to Z1, Z2, Z3. In other words, there exists some constants, the Lagrange multipliers. Oops, that's a different constant. Such that that is true. Okay, so I know what alpha, beta, gamma is. Okay, so step 2. Step 3 is I can reshare the resulting full threshold. So this is what's called a full threshold sharing. Look, this looks like a full threshold sharing of the product, yeah? Because party 1 has Z1, party 2 has Z2, party 3 has Z3. So in some sense, what I've got is I've got a new values that party 1 computes, which we'll call T1. Whoops. T1. This one we'll call T2, and this one we'll call T3. So that looks like a full threshold sharing. Okay, so that's step 3. So I haven't really done anything yet, have I? Now, step 3, now what I do is I take the T1, the player T1, and he's going to reshare that using Shamir. So what he does, so step 3 is player 1 computes the sharing T1. So he generates a new polynomial of degree 1, yeah, because we're in nt is 1, which is going to be, so player 1 does this, and we'll call that h1 of 1, h1 of 2, h1 of 3. And then instead of he keeps h1 to himself, and he sends that to player 2 and that to player 3. If we do this, player 2 does the same with T2, so he produces another polynomial h2, of which shares T2. Okay, he keeps h2 to himself, he sends that one to player 1, and he sends that one to player 3. Okay, so what do we now have? Well, we now have, and this is where the board's really good, and if you're taking notes, it's more complicated. I now have a secret sharing of Z1, Z2, and Z3. So I can just put square brackets, T1, T2, and T3. So I could just put square brackets around this thing, which means I now have the square bracket sharing of S times S dash, and I'm done. Yeah, so I've multiplied. Yeah, so because what I've done is my input was a secret sharing of S, a square bracket sharing of S. My input was another secret sharing, square bracket sharing of S dashed. And with these 4 steps, I've got a secret sharing of S times S dashed in the same secret sharing scheme as what I started with. It's got a different polynomial. No one knows what the polynomial is which shares it because no one knows what the product is. But I've computed the sharing, and I've used basically what I've done is I've used the fact it's multiplicative, allows me to do step 1 and step 2. I've got the product is actually the linear is essentially a full threshold sharing of the Schur products via the Schur products. And now what I do is I can now reshare the thing again, and that allows me to then do the combination trivially, which gives me the sharing of the product. Okay, so I can now do multiplication, and I'm done. So I'm really, really happy. And here we go. This is all in slow motion. Da, 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 da. I used U there rather than T, but there we go. And blah, blah, blah. And then I could also do it with replicated secret sharing if I particularly want to as well. And it all just works. And so I can now, I'm information theoretically secure. If half of you are, if under half of you are corrupt, then the rest of you are happy, right? So I don't care, but you lot are happy. Okay, right. Okay, so that's quite cool. And but that's just one way of doing secret sharing. One way of doing multiplication. So what my MPC protocol will end up being is I'll take my function, I'll represent it as basically 4 operations: input, add, multiply, and output, which is basically like that. So the parties input by just secret sharing their inputs. They add, they multiply, and from when you want to get an output, you just recombine, and you're done, and that's it. And this is passively secure MPC. It's relatively fast. For example, linear functions are just as fast as linear functions as they would be in the clear, and multiplication requires interaction. So it's only passively secure, which is a problem. It's only passively secure, and the part of the problem is that I actually have to represent my function as an arithmetic circuit, which can be a bit of an overhead. It's only polynomial overhead, but yeah, but it can be a bit of an overhead, but not much as an overhead as FHE is. Okay, so this is just purely, this is real polynomial overhead. You know, you could actually compile things down and there would be a polynomial overhead. It's not that hard, just gives you a bit of a slowdown. Okay, so that's this multiplication protocol. There are other multiplication protocols. There's a multiplication protocol due to Damgard and Nielsen, which is on the slides, but I'll just click over because it's not really that interesting. But the more interesting one is what's called Beavers Method. So we'll click over these ones. So Beaver multiplication is slightly different. So in Beaver multiplication, what we do is that we assume that there's some magic process which allows us to generate sharings of random triples, so-called Beaver triples. So we've got a sharing of A, a sharing of B, and a sharing of C, such that A and B are random, unknown to anybody, but C is the product of A times B. Okay? So just assume there's some magic process that gives us these things. Now, if we have that magic process, however magic it is, then we can also do MPC when we've got full threshold, and you're now happy again. Okay, so we can now do arbitrary access structures if we can produce these triples. So we'll come to at the very end how to produce these triples, but let's just assume for the moment they're magically created. Now, if they're magically created, we've got this lovely secret MPC protocol, which is what's called Beaver multiplication. And here, what you do is you again use the fact that we reduced multiplication back to linear functions. But somehow we need to introduce some form of nonlinearity into it. And the nonlinearity is introduced by the fact that the Beaver triple is itself nonlinear, because C is equal to A times B. So what you do is you take the values you want to multiply, secret shared. So you subtract from X the value A, and you open it. Well, that's basically a one-time pad encryption of X under the key A. So we better not use A again. Okay? So we've just spent it. Now we do a one-time pad encryption of Y under the key B, and we open it. We call it delta. So epsilon and delta are now publicly known. And then we just compute that linear function. And if you do the maths and expand out the values, you'll find that that linear function ends up being X times Y by the magic of maths. It's kind of cool, isn't it? So you kind of like, yeah. So it's kind of like, so we just do a couple of openings and a linear function if we've already computed these Beaver triples, which is kind of cute. Okay. So we're done. If only. Then you'd be able to go to the bar. Nice one over the road, so it was new. Okay. Right. Okay. So the problem is we've only talked about passive security. What we really want is actively secure protocols. Okay. So the traditional way of doing this in the dim and distant past, 1990s, was to use something called verifiable secret sharing, which required us to have linear secret sharing schemes which are strongly multiplicative, and it was just a mess, and it was just not very efficient. Okay, so no one does that anymore. No one. No. Unless you want robust protocols, but no one wants robust protocols because we'd have to do this and it's really slow. That would be silly. Okay, so we want a better method. Now the better method is to ignore this robustness stuff that the theoreticians worry about and actually go for active security with a bolt. And so we don't want to correct the error, we just want to detect there is one. And so what could go wrong? Well, if we look at the Beaver thing, the things that could go wrong is the triple could not be a triple, but we've swept that under the carpet for the moment, so let's not worry about that. But the only thing that could go wrong is you lie about x minus a. Someone lies about x minus a, so you actually recover the wrong epsilon. Yeah, so it's the only thing that actually happens is people say, this is epsilon, this is delta, yeah, and if they could lie. Okay, so what we want to do is stop them lying. When you open data, we want to stop you lying. And how do we stop people lying in cryptography? We add a message authentication code, yeah? So it took 20 years to come up with that idea, so it's quite deep, isn't it? Anyway, so what we do is we just add a message authentication code to everything, okay? And then everything's easy, okay? And there's different ways of adding the message authentication code. So the way we're going to do it is working backwards. The first protocol I'm going to show you to become actively secure is actually a protocol due to Chida, Genkin, Hamada, blah, 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 from last year, okay? Because this one is easier to understand than the one that's going to come up afterwards, okay? Which is the older one. Now, the disadvantage with this one is we need to be able to do passive multiplication protocols, okay? So we're not going to combine this with the Beaver thing yet. We're just going to take the Maurer multiplication we did, like for Shamir, and we're going to try and make Shamir actively secure, and we can see how this works. Okay, so what we're going to do is instead of so we're going to take elements in the finite field are going to be shared with respect to this secret sharing scheme. Again, it's going to be square brackets. We can perform linear operations on those, tick. The problem is we've only got a passively secure multiplication protocol. And that's the only bit where people communicate, so that's the only bit where they can lie and we need to detect cheaters, okay? So that's the only bit we really need to protect. And we're after an active security with a bolt protocol. Okay, so what's the basic idea of this protocol from last year after 30 years of research? Is basically add a message authentication code. Is what you do is you take a key alpha, okay, and every time you want to authenticate the value x, you also have a value gamma, which is alpha times x. And this is authentication code. So alpha is the key to the code. Gamma is the tag value, okay? But the problem is we want to verify these tag values without revealing x, gamma, or alpha. So we're going to verify the max without actually seeing the MAC tag, the value being MAC'd, or the key. Okay, so that's the tricky bit, but the rest of it is, let's assume we can do that for the moment, okay? So every time we just move the impossible to somewhere else. Okay. Okay, but let's assume we can do this, but the point is you can't then change x without knowing gamma or alpha or both. So it's impossible to make a change on some data unless you change something else, and you can't do that because you would lose track of what you're changing. Okay, so the idea is we first set up a key alpha that no one knows. So everybody generates an alpha I. We enter this into the secret sharing scheme. We add them up, and we've all now got a sharing of alpha that no one knows what the alpha is. Okay, tick, that's easy. Now, every time we're going to operate on a value x, instead of operating on a secret shared value of x, we operate on a secret shared value of x and a secret shared value of alpha times x. Yeah? So we just doubled the amount of stuff we have to do, but who cares? Because we haven't really done much anyway, right? So we could do this via PRSS, but that's slides I'll skip over later. Don't worry about that. Okay, So if the square bracket sharing, that's the original one, the Shamir sharing, say, is linear secret sharing scheme, then so is this super duper sharing with the MAC value as well, because do you know what? It's all linear, therefore linear functions are just going to be linear, yeah? So we can still, with the angle brackets, we can add constants, and we can do multiplication by constants. So that's all the same. And then if we want a passively secure multiplication protocol, we just execute the passively secure multiplication protocol twice. So if I want to compute the product of angle bracket x and angle bracket y, I execute the passive protocol for square brackets once, and then the passive protocol for square brackets twice again, yeah? And I've now got the angle bracket, which contains the MAC value as well as the actual product. Yeah? So that's kind of cute. So I can do additions, I can do multiplications. What else can I do? I'm not going to talk about checking the MAC value yet. That's pushed under the carpet for a bit, okay? So as we keep pushing things under the carpet, I can generate random values. It's brilliant, right? I can, if you want to generate a random value, everyone just enters some random values. We now execute the passively secure multiplication protocol to get alpha times r. I've now got a random sharing in the square in the angle bracket notation of a random value. So I can do, again, you can replace that as well. PRSSS. I can input values. So if I give you a random, once I've got a random authenticated value, angle bracket r. If we just open, if you want to enter a value, okay, so you're entering a value. So what we do is we all open our value r to you. You now have the value r. You subtract it from the value you actually want to enter into the computation. So r is like a key for a one-time pad that only you know the key now, r. And now we've got x minus r. We now broadcast x minus r to everybody, and we now add back on the angle bracket of r. And that's now an authenticated value of x. Yeah? So we can actually enter stuff into the computation as well. Okay, so we can enter stuff, we can produce random values, we can multiply, we can add. So all with passively secure protocols. So the only thing we have to do is check that when we execute those passively secure protocols, everything has happened correctly. Now the only thing that the adversary, if he deviates from the protocol, the MACs won't align. The MACs will be wrong. Because essentially information theoretic is that the only way you can change the MAC in a valid way is also to change the key. And you can't change the key because you committed to the key at the beginning. So you would have to kind of know the relationship between the value that you're changing and the key to be able to produce an equation which allowed you to change it without breaking the MAC verification equation. So what we need to do is just check, or we can also output values, but that's easy, don't worry about that. So what we need to do is we need to check that the MAC values are correct. And this is the simple protocol we use to check the MAC values are correct. So we've got a bunch of values that let's go back, right. So what we've done is we've got a bunch of input wires and a bunch of output wires of all the multiplication gates. So what we do is they're all the values that have been broadcast. So to check they're all correct, what we do is we take a random sum of the linear of the stuff, which we can do because that's a linear function. We now take a random sum of the MACs, and we just check that the random sum corresponds to the random sum in the correct way. So we compute this. We now open the MAC key at the very end of the computation. We verify here, and then we check that we've got 0 or not, and that the MAC verifies. Okay, so at the very end, we reveal the key and then verify the final MAC equation. And if all's okay, then we've got a actively secure protocol. And it's trivial, yeah? And what's even more better than this is that if you think about it, what we've done is we've got a passively secure protocol, multiplication protocol with Mara. Now what happens is to make an actively secure protocol, we just basically double the cost. We have to, for every multiplication, we have to do 2 multiplications. For every data entry item X, we have to hold data item and the MAC. So we just doubled the amount of cost, but then verification that everything's okay is trivial and is done at the very end in an amortized manner. Yeah. So the cost is only double the cost of essentially computing in the clear-ish, in theory, asymptotically, maybe, and ignoring communication costs, but let's not worry about that at the moment. Yes. So, but in comparison to the way it was done before you had these ideas of using the MACs to verify the computation, where you needed to use verifiable secret sharing and have robust protocols, there the cost of doing the evaluation was orders of magnitude more expensive than doing just the passive protocol. So here what we have is that the complexity of doing active security is a marginal overhead on the complexity of doing passive security, which is kind of a big win. Okay. Oh, I am going to get to the cool bit. Okay, so that's good. Right, so what we now have is we have a protocol which is twice as expensive as passive. Now that might be good in some applications, but what we really want is we want a protocol that's fast when we need it. Yeah, imagine you're a bank and you're processing lots of data. You only process data during the day because that's the only time your customers are awake, yeah? During the night, you've got your servers just processing the rest of the day. It's the way banks operate. They take in data during the day and they process stuff at night, yeah? This is kind of why it takes ages for your payments to go through the system. You have to wait for the nighttime upload and the gross settlement to happen, yeah? So, and other companies are like that. You have stuff that works during the day and stuff that works during the night. So you could actually offload a lot of data to your nighttime operations to make your daytime operations go faster, to be able to respond quicker to your customer. So there, what we had in the previous protocol is it took twice as long to respond actively in an actively secure way than in a passively secure way. Now, what happens if we could offload some stuff to the night time such that during the day we could respond without that extra doubling of cost in the execution, yeah? So can we be faster when we actually want to be? So this is what's called the online-offline paradigm, pre-processing model versus non-pre-processing model. Okay, so in the previous protocol, for each actively secure multiplication, you had to execute 2 passively secure multiplications. Now, what we're prepared to do now is go a little bit, only a little bit slower overall to make the online much, much faster. Okay? And the way we do that is we use the Beaver triples. Okay? So in the offline phase, overnight, again, we're pushing stuff under the carpet till later. Online, overnight, we're going to produce the Beaver triples. And then in the online phase, we're going to consume the Beaver triples, and they're very fast. Remember, there's nothing happening there. You just open some stuff and linear combination, open some stuff, linear combination. Okay? And unlike in the previous thing, we're also going to be able to cope with the fact that everybody bar one is dishonest. Okay? Because the previous protocol of Cheetah et al. Required us to have honest majority because we're using Maurer's multiplication. Okay, so how are we going to do Beaver's method? We just do Beaver's method, right? So we just replace all of the square brackets we had earlier by angle brackets. And with the power of LaTeX, I can replace all of the angle brackets, all of the square brackets by angle brackets, and suddenly I have a Beaver multiplication protocol for the authenticated secret sharing of the angle bracket protocol. Okay? So that's kind of cool. And then here I could just open the values, not the MAC. Here I just open the value, not the MAC. So at the end, what I'm going to do is I'm going to verify using the kind of MAC check protocol that this epsilon you actually opened correctly. Yeah, because if it didn't open correctly, its MAC that we don't know anything about yet would be wrong. Okay? So I stop you lying in this stage of the Beaver protocol by later at the very end checking the MACs. Okay. So now what I need to do is, so again, let's assume I have some passive multiplication protocol to produce the thing squarings. So what I now do is I want to now produce the Beaver triples. Now I produce the Beaver triples by just executing the passive multiplication protocol. But then what might happen is that I might lie when producing the Beaver triples. Yeah? So the C might not equal to A times B, which would be a bit of a problem. This is overnight. So now what I could do is I could actually check whether the Beaver triples are correct by a method called sacrificing. So suppose I've got 2 sets of Beaver triples, A, B, C, and F, G, H, and I want to confirm that C equals A times B, that I haven't lied when I've produced A, B, C, and F, G, H by the passive protocol. So again, what I do is I now just do some magic of maths, and here I can check that actually C does equal A times B and H does equal F times G, because if it didn't, E would never equal 0. Okay, so I can check via sacrificing whether the protocol is valid or not. Yeah, whether my Beaver triples are valid or not. Okay. Dum-de-dum-de-dum. Okay. So that's sacrificing. And then I could just do MAC checking like I did before. I could reveal the alpha. But the problem is if I reveal the alpha, I can't actually compute anymore because I've just lost my MAC key, and my whole security was based on the fact that my MAC key was secret. Yeah? So if my protocol for checking the MAC reveals the MAC key, then I'm a bit screwed for later on. It's okay for this execution, but I can't do more computation. So if I was running some sort of reactive computation in an organization, I computed some function on the database, and I went, oh, there's the average age of people who have cancer is X, and now I want to know what's the average age of people who have heart disease. I'm screwed because I've just lost all security because I've just lost the MAC key. Yeah. So what I want to do is be able to check the MAC without revealing the MAC, and we could do that as well. So we just check the values open during sacrificing, check the values open that we opened during the multiplication protocol, and we could check withhold correct shares without revealing the MAC key at all, and we do it by a similar trick to what was in the previous protocol. So there's nothing really new there. Okay. Right. Okay, I'm going to skip this. It's a bit dull. They're very dull. Okay, so now we're going to go back in time. So Cheetah's result was that if you had honest majority, you could get actively secure MPC, where you had twice, for every secure multiplication, you had to do 2 passively secure multiplications. Okay? And then what we said was, well, if we could produce Beaver triples in some arbitrary offline phase, we haven't worked out what it is yet, we could actually produce an MPC protocol in which the online phase was virtually no additional cost to computing in the clear, bar the communication, which we'll not worry about. Okay? And this is actually a protocol that goes back to 2012. It's called Speeds, because it's me, S, Padro, Damgard, Zacharias. So it's called Speeds, okay? So, because it goes fast. This is, when this came along, it made everything else instantly obsolete. It was just like, it's so much faster than anything previously anyone had thought of was possible. Asymptotically, it's faster, blah, blah, blah. Okay. Okay, so how does Speeds work? The Speeds works just as we've just said. We have, we're going to have additive, a complete full threshold. So now you're happy. You can process without worrying about how many bad people there are in the room. Okay, so this is really good. So this protocol is secure irrespective of how many bad people there are. So imagine this protocol comes along, which is A, faster than anything that went before, and B, more secure and copes with worse adversaries than anything that come before. It's kind of like really cool. Okay, not mainly Damgard's idea, it must be said, not mine. But anyway. So what happens is that we have this MAC key, which we just secret share additively as alpha 1 to alpha n. Just like we had essentially before, but now we're just doing it with additive secret sharing. And if we want to hold a secret shared value, we do just like we did before. We hold x and alpha times x. There's no difference here, yeah, which is exactly the same as in Cheetah's protocol. What we're going to do is, if we want to share a public constant, we can share public constants. This is now easy. If we want to do addition, we can do additions. We've seen this endlessly. This is now boring, yeah? It's kind of like, come on, get on with it, Nigel. Okay, multiplication, we do it via Beaver triples. We've seen this. This is the third time you've seen this slide. There's just got a small minor change here because it's now the Speeds protocol. There's nothing different, yeah? This is all very, very standard. Okay. Now we've got a problem. How do we produce the Beaver triples, I hear you ask? And then that's where the trick comes in. And this is why it's 2012 and not 1986 or something like that, okay? Or 1990 or something. Because what we're going to do is we're going to use homomorphic encryption. which you're going, but that's slow. You said that takes a long time. There's big constants. We'll be dead by the time it's finished computing. No, because what I said was if you want to compute an arbitrary function, you'll be dead. If you want to do Google search, I said you'd be dead before you got the answer, okay? Here, we don't want to compute an arbitrary function. We want to compute a really, really, really tiny one. Really, really tiny. So tiny it's almost indistinguishable from nothing, okay? Almost. Okay, so what we actually want to do is all we care about is multiplicative depth 1. I only want to compute one multiplication and a few additions, okay? That's easy. Yeah, how hard can that be? It's not very hard at all. And also to make things go super duper duper fast, we use a technique of myself and Frey, which we call SIMD execution, which is just a really, really deep way of saying Chinese remainder theorem, okay? We published a paper on this, and Frey was going, why are we publishing this? It's just the Chinese remainder theorem. And I went, well, but the people reading it won't know that. And it's got lots of impact, and it's got 400-500 citations for what is basically the Chinese remainder theorem, okay? So never ever put down what you can repackage, yeah? It's all in the spin. Okay, so by respinning the Chinese remainder theorem and saying it's SIMD for homomorphic encryption, you can get huge performance speed-ups, absolutely huge performance speed-ups, tens of thousands of times faster than previous, okay, just by Chinese remainder theorem. Who would have guessed, huh? Anyway, so we just want to do multiplicative depth 1. And so how we do this is quite simple, is that we assume we've got this distributed decryption algorithm. That was at the beginning as well. It's almost like come full circle. It's like a unique whole, this lecture, isn't it? It's kind of gives you completeness when you finish it. Anyway, so what we have is that what we do is that if we have this distributed decryption algorithm, we have an algorithm that allows us to produce resharings of encrypted values. We can translate between an FHE encryption and a secret sharing encryption, where if you think of secret sharing as being a form of encryption. How do we do this? It's a protocol called reshare. So what we do is we have a ciphertext that encrypts a message M. At the end, what we want out is an additive sharing of the message. Just M1, party 1 holds M1, party 2 holds M2, party 3 holds M3, and so on, such that the sum of the MIs is equal to M. Okay, so how we do this is each party generates some random stuff and encrypts it. That's easy. We now compute the ciphertext we started with plus the sum of all the ciphertext we just got. Now, if we think of each Fi as summing to F, so F is F1 plus F2 plus F3 plus blah, 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 okay, then the ciphertext, this ciphertext is actually the encryption of M plus F. Okay? Okay, let's just distributed decrypt this and get M plus F. But no one knows what F is. I know what F1 is, you know what F2 is, you know what F3 is, but no one knows what F is. So F is a one-time pad key for the encryption of the message M. So this is a one-time pad encryption. Tick. Okay, so that's good. So that tells us nothing. Now, party 1, he knows F1. So he just sets his share M1 to be M plus F minus F1. Party 2 sets his share to be minus F2. Party 3 to be minus F3, and so on. And then if we add up all those MIs, we get M. Haha, it's cool, huh? Very cool. Yeah, so this is cool. And then if we actually wanted a new encryption of the message, for some reason, that we might have on the next slide, we want a new encryption of the message, we just encrypt M plus F again, and then subtract the things we started with. This is to allow us to only use depth 1 circuits. We can basically, this we might have spent our homomorphic encryption when we've got our ciphertext here. Homomorphic encryption can only encrypt up to a certain level. Yeah, you do. Oh, I'm allowed one encryption. Oh, can't do any more. But now I want to bring it back down again to allow me to do another encryption. Okay, so I do this by I've got this encryption of CT where I can't do any more multiplications. But this is a fresh encryption. These are fresh encryptions. So this CT dash encrypts the same data as CT dash, but it encrypts it in a way that allows me to do more multiplications. Okay? So it's kind of a little trick. It's almost like bootstrapping, but using distributed decryption to do bootstrapping. Okay, So how do I generate a secret sharing in the angle system of A for my Beaver triple or B? What I do, every party comes up with some random AI. They encrypt it. This gives, and then we add all those encryptions together to give us an encryption of A, where we know the plain text is equal to A1 plus A2, blah, 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 blah. Okay? Now, we've got an encryption of alpha, so we can now use the FHE property that we can do one multiplication. So we now get an encryption of alpha times A. Now I execute reshare on that product alpha times A, so everybody obtains the MAC key, or the MAC value, their share of the MAC value. Yeah. So this gives us, so this allows us to generate sharings of random values in the angle bracket notation. Tick. And we repeat the same thing with B, so that's good. So how do we do C? Well, we've got an encryption of A and an encryption of B. I want to produce C, which is A times B. So what do is I multiply the ciphertext encrypting A by the ciphertext encrypting B to give me a ciphertext encrypting C. That's that. Now I can get the sharings, I can get a sharing CI by running the reshare protocol, but also obtain a fresh ciphertext, which allows me to multiply by alpha to run this reshare protocol to allow me to get the shares of the MAC values on C as well. Yeah. So this is how, so this allows me to produce Beaver triples to my heart's content. Okay. And this allows us to, okay, so this is cool. That's it. I mean, there's almost left. Okay, one bit I have put under the carpet because it's really complicated and I don't want to get into it, is that you can still lie. Okay, the problem is that this protocol, so this works. Everything I've said works up to this point. So the only bit I've lied about left that I haven't told you how to do, and I'm not going to tell you how to do, is the following. Where am I going to do it? Here. Okay, each party generates a random AI and transmits the encryption of AI. Okay. How do I know that's a valid encryption? Okay, so when I encrypt with El Gamal, every element in the group C1, C2 is always a valid ciphertext. There's some message I don't know. If I encrypt it with textbook RSA, every element in the integers mod n is a valid ciphertext with overwhelming probability. Yeah, Zn. If I do Z mod n Zn star, nz star, then everything is a valid ciphertext. But with homomorphic encryption schemes, it's not true that everything is a valid encryption. Yeah, so I have to prove that I've encrypted something validly. Okay, and that turns out to be the only thing that's tricky, and it's not actually that tricky because now we can do that bit. So that was in the past 10 years ago. Oh my God, no, yeah, no, nearly 10 years, no, 8 years ago when we first came up with this. That was the really fast, that was the really slow bit. Now that's so fast that the slow bit is actually doing this, just doing the homomorphic multiplications. So the rest is relatively fast. And if you want to play with the software, you can download it from the COSIC website and play. And it's got a programming language, and you can build your own MPC protocols out, etc., etc. So with that, I am going to end it. And there's any questions, otherwise you can go for your beer 10 minutes earlier. Thank you.